Ever notice those number patterns that just seem to zoom off or maybe shrink consistently?
Uh,
Like, think about how something goes viral online, maybe doubling each hour, or maybe a value depreciating by, say, 10% each year.
exactly. They're not just random numbers. There's often a specific rule underneath.
And that hidden rule, that pattern, is what we're diving into today.
Yeah, we're looking at sequences, and specifically a really neat type called geometric progression. You'll often see it shortened to GP.
Right. So a sequence is just basically a list of numbers in order following some rule.
Exactly. Our source material gives a few examples like 2, 6, 18, 54. See how you're multiplying by 3 each time? Or 1 minus 12, 14 minus 18.
Okay, that one's alternating signs.
Right, you multiply by negative 12, it flips the sign and has the value. Then there's like 6, 4, 2, 0. Different again, subtracting 2 each time. That's an arithmetic progression, actually.
Good distinction. And sometimes you hear series instead of sequence. What's the deal there?
It's a subtle difference, really. A series is just when you take the terms of a sequence and connect them with plus or minus signs. So like 2 plus 6 plus 18 plus 54 plus and so on.
4 minus 12 plus 14 minus 18.
Exactly.
Oh.
But honestly, for understanding the core pattern today, that GP pattern, the distinction isn't super critical. We're focused on the rule generating the numbers.
Gotcha. So the main event is geometric progression, GP. What's the absolute key idea?
The key is that constant multiplier. To get from any term to the very next one, you always multiply by the same fixed number. Or you could divide, but dividing by, say, 3 is just multiplying by 13.
Right.
And that fixed number, that constant factor, that's the heart of it. We call it the common ratio, usually written as R.
Okay, so our mission for this deep dive, really get a handle on these geometric progressions, understand the core ideas using the material we've got.
Let's do it.
So what truly defines a GP? You mentioned the common ratio.
That R value, yeah. That's everything. Let's look at a few more examples from the sources. We saw 2, 4, 8, 16.
Easy one. Doubling each time, so R is 2.
R is 2, exactly. Then 6, 2, 23, 29.
Okay, getting smaller. 2 is 1/3 of 6. And 23 is 1/3 of 2.
You got it. So here R is 13, like shrinking consistently. And one more, a bit trickier. 60, negative 24, 9, and 35, negative 3, and 21, 25.
Whoa, okay. Signs flipping again?
Yeah. If you work it out, negative 24 divided by 60 is negative 25. And 9 and 35, which is 485, divided by negative 24 is also negative 25.
Ah, okay. So R is negative 25. The negative ratio causes the signs to alternate.
Precisely. And finding that R is straightforward, just take any term and divide it by the one right before it.
Like in the example, 16, 8, 4, 2, 1, 12.
Yeah, do 8 divided by 16, that's 12.
4 divided by 8.
Still 12.
1 divided by 2.
12 again.
Okay, so it's consistent. R equals 12.
And that's the beauty. If someone gives you the first term, let's call it A, and the common ratio R, you can generate the whole sequence.
Right, like if a 5 and R is 3.
You start with 5. Then 5 times 3 is 15. Then 15 times 3 is 45. Then 45 times 3 is 135, and you just keep going. 5, 15, 45, 135.
Or write it as a series. 5 plus 15 plus 45 plus 135 plus... Okay, this makes sense. But say I wanted the 20th term or the 100th term. Multiplying it out that many times seems tedious.
Oh, absolutely. That's where a formula comes in super handy. The general term formula. Let's stick with A for the first term and R for the common ratio. The first term, we can call it $T, is just A.
Right. $T is a dollar.
Now, we can also write A as A times 3 to the power of 0. $8, because anything to the power of 0 is 1. So $T is R1.
I see where you might be going.
The second term, $T, is the first term times R. So $2 goes R. Or we could write that as RR. The third term, T3, is 22 times R. So $AT, which is R3.
Right.
R3.
I see the pattern. The term number, say N, matches the N in the exponent part, N on us. So the nth term formula must be 8 times star to the power of NS.
You nailed it. T-S, that's the general term formula. It works for any term.
That's powerful. So for the first term, N1, $1, N1 is R, For the second, NR, 21, R11. Perfect.
Exactly. And one more thing. If the GP actually stops, if it only has, say, n terms in total.
Then the nth term is the last term.
Precisely. So we often use the letter L for the last term. In that case, 1 dashed R1.
So if I want the 8th term, like you said, I don't need the first 7. I just use the formula.
Yep. For the 8th term, N8. So 8 terms in 8 says 8 Ron are for these 3.
15th term?
R14.
20th term.
Simple as that.
Okay, this is great. It feels like if I know any 3 of those things, A, R, N, or the term value, $2, I can probably figure out the 4th one.
That's exactly right. The formula connects them all. Shall we try identifying some GPS using this idea? Example 1 in the source gives us a few sequences.
Let's do it. First one is I2, $2.42, 4, $4.42, GP or not.
Okay, we need to check the ratio. Second term divided by first. $2.42, 2.
We're the next pair.
$4, $2.
Uh-oh.
Well, 42.2 is $2 core, so it's $2.42 down the turn to rationalize.
You get $2.42, which is just Psycher 2 Hey. It matches.
Okay, one more check. Fourth term divided by third. $4 squared to 4.
They're all scored, so yes, it's a GP common ratio 1:143.
They're all scored, so yes, it's a GP common ratio 123.
Okay, second term, first term, 23, 1 equals 23.
Good. Third term, second term, 123.
That's 32.
Or 23 and 32 the same?
Definitely not. So this one's not a GP.
Correct, no constant ratio.
Okay.
Next 3, 4, 8, 16 times.
8, 4, 2. 16, 8 was 2. Look like a GP with R2.
Yep. And the last one, brush through 60, Y42.
Okay. 6 by 2, y by 2 thars.
Right.
The y's cancel, the y d12 is just x.
And then X pair.
60y by 2y, 2y. Again, y's cancel, 6, 3 by 2, 2 is x.
So?
It's a GP with common ratio r, x, assuming x and y aren't 0, I guess.
Good point, yes.
Yeah.
Assuming X is not 0. Okay, ready to use the formula $2, R, and 1 to find specific terms.
Let's go. Example 2. Find the 8th term of 5, 10, 20.
All right. First term, A.
A5.
Common ratio R.
And we want the 8th term, so n.
And 8.
Okay, plug them in. $8 times run in 1, 5 times 2 in 1.
That's $5 times $27. $27 is 2 to 5 i's is 32. 2 e's is 64. 2 7 zetas is $128. Right, so 8 Taylor's rule 5 times 120 80s.
Which is 640.
Nicely done. Okay, example 12 looks a bit more intimidating. Find the 19th term of the series, Gort 3 plus Frank was Franklin.
First, is it even a GP? Let's check the ratio. Second term over first, $1.
33 times
Third term over second, 1 squared 3, so rest cancel.
He can do it 13.
Phew. Okay, it is a GP. So RU1, the larding $13, and we want NNEL1.
Exactly. So T19, RNE9 starts $19.
Which is RN1 and LEO. Can we simplify that much?
We can write it as a Gort 3 too. That's probably the neatest form.
Fair enough. Example 4. First two terms are 125 and 25. Find the sixth term.
Okay, first term, 8R and 25. What's R?
First term, 25, 125. That simplifies, divide by 25 gives 15.
Good. So R15. We want the sixth term, so N6.
Right. $6 are $6 are $6 and 55.
Okay, 15.55 is $1. 15.3. 503.3 is 125. 543 is 625. 525 is $3,125.
Wow. So $6 equals 125, 325 5 times. So maybe it goes into 325 times, 25 times.
Let's check. 125 times 25 times 1,004.
Right.
1,2504 equals 125 times.
Yes, so it simplifies to 125.
Perfect. Example 5 is slightly different. Find the next three terms of 36, 12, 4.
Okay, first find R. 2RR, so 336 equals a 6 to 33.
Yep.
So the sequence continues by multiplying by 13. The last term given is 4. What's next?
$4 times 13.32.
Good. That's the fourth term. What's the fifth term?
43 times 13 equals 49.9.
And the sixth term.
$49 times 13 equals $49 times 13 is 427.7. So the next three are 43, 49, 427.
Excellent. No, example 6 flips the question around. Which term of the GP3, negative 6, 12, minus 24 is negative 384?
Okay, here are 3. The ratio R negative 6, 3, negative 2. Let's check. 12 negative 16 equals 2.
Good. We want to find the n such that $2 equals $384.
So we use the formula. T net equals R n now to 1. That means $384 is 3 times n is to 1.
Right. How do we solve for n? First, maybe divide by a.
Yeah, divide by 3. Negative 384. 3 negative 128. So $128 equals negative 2 nexus.
Now we need to figure out negative 2 raised to what power gives negative 128. Let's try powers of negative 2. 23 thins is a 5 1 months, and 3 and 83 fourths, and 2 thins is 47 but 1 months and 20 over 2. Times is the anzay 70 of all, then it's except for 780 to where and as it falls, the len is $228. There it is.
So the experiment we need is 7.
That means n of 4 must equal 7, which means n equals
and 8. So negative 384 is the 8th term.
Fantastic. Last one in this batch, example 7. Find the GP whose 5th term is 48 and 8th term is 384.
Okay. We don't know A or R, but we have 2 pieces of info.
Look, what is 5th term is 48? Tell us using the formula.
Phi dollars are 5-1, R4 on 4 are the 4, so R4 R1, R4 2 so R488 4-2. Second equation.
2 equations, 2 unknowns, A and R. How can we solve this system? Dividing seems like a good idea here.
Yeah, let's divide the second equation by the first one. R4 R 384, R4 R4 water 484.
What happens on the left side?
The A's cancel. $7 R4 R4 R is close to 50. 384 is close to 400, maybe 8. Let's check. 48 times 8 is 2 times 8 times 80, 416 equals 82.
Which means R must be
the cube root of 8, which is 2, so R2. Yeah. Great. Now we need A. We can use either equation. Let's use the first one. R is $4 equals $488.
Okay, substitute R2. R times 2 for what was 488. $284 is 16. So $16 is $408.
And divided by 16 gives?
A 3.
So we found a 3 in R2. The question asks for the GP itself.
Right. So it starts with 3, then $3 2 equals 66, then $6 times 2 is 12, 2, then 24, and so on. The GP is 3, 6, 12, 24.
Exactly. You've got it.
Okay. Finding individual terms makes sense now. The source then talks about the product of terms. Example 8. If the third term is 4, find the product of the first 5 terms.
Right. So we know $3 were to R. In terms of A and R, what is 3, 3?
$3 are through R3, $2 are R2, 2. So
$3 are R2 times R2. So
times R2 times R2 times R3.
Okay, combine all the A's and all the R's. How many A's?
There are 5 A's, so 5, 5.
And the R's. We have $3 times R2 times R3 times R4. Add the exponents. $1 plus 2 plus 3 plus 4 plus 10 does. So
the product is AR10. How does that help? We only know R2, well, it's 4, 2, R2.
look closely at the product. A of R10. Can you relate it to R10 too? Think about powers.
Hey R10. Wait, is that the same as R2 raised to some power?
Let's see. If you bar 5 times A5 times A5 times A5 times R2 times A of R10, yes.
It is. So the product is just AR2 5, and since we know R2 off 4 2, the product is $45.
And 45 times 5 is $42, 43 R's, and 6 4 3 side 4 4 no 44 5 2 is 45 5 or known to R2 4.
So the product of the first 5 terms is lay now 24. That's pretty neat how it worked out.
It is rather elegant. Okay, example 9 is about finding R given some conditions. First term is 1, and the sum of the third and fifth terms is 90.
Find R.
Okay, a third term, $30 par 3 1 1 times R2 R2 2.
And the fifth term?
$5 SAR 5 1 1 times R4 is R4 8.
The sum is 90, so...
$2 plus RP hour is 90.01. How do we solve that? It looks kind of like a quadratic equation.
It does. If we let, say, 6R2 is by 22, what does the equation become?
Then R22 would be R22 F by 2 2. So the equation is 6 doubles plus by 2 A pulls by 2 2.
Let's rearrange that into standard quadratic form. 6 by dollars plus by 90 plus is dollars.
Can we factor that? We need two numbers that multiply to 90 and 90 and add to plus 1. How about plus 10 and 99?
$10 times 99 is 9 plus 90 is not perfect. So it factors as 6 is plus 10 by 9 to 9 quarts dollar.
That means either 6 plus 10 by 9 to 9 is 9 or 6 is 99.
Right. But what was X again?
6 was R22. So $20 equals 10 or $20 is equals 99.
Can 22 be minus to 10 if R is a real number?
No, squaring a real number always gives a non-negative result. So $20 is impossible here.
Leaving us with
$20 is 99. That means R could be 3 or R could be 9 to 3.
Exactly. Two possible common ratios fit the description.
Interesting. Okay. Example 10 looks at a property. If the 4th, 7th, and 10th terms are A, B, and C, respectively, prove $2 equals easy caller.
Right. Notice the term positions. 4th, 7th, 10th, they're equally spaced, right? 7, 4, 3, and 10, 7, 3.
Good point. Okay, let's use capital A for the actual first term and capital R for the actual common ratio, just so we don't mix them up with the A, B, C in the problem.
Good idea. So the fourth term, which is A in the problem statement, is...
AR41, AR42.
The 7th term B is...
And the 10th term C is...
And the 10th term C is...
BR10, Tellens 1, and NIR 99. Okay, now the property we want to prove is $2B, A equals... Let's calculate both sides using A and R. What's $2B?
$2B at AR62 equals A2 times R62 until A2 R12.
Okay, now what's the product's A call?
AR3 times A times A times R3 plus 9 equals A2 R12.
Look at that.
They're identical. $2B A2 R12 and A2 R12C, so $2B be proven.
Exactly. And this holds generally. If you take any three terms in a GP that are equally spaced apart in terms of their position number, like 4th, 7th, 10th, or 2nd, 6th, 10th, the middle one squared will always equal the product of the first and the third.
That's a really cool property. It's like the geometric mean idea.
Precisely. It's closely related.
Okay, now the source talks about finding terms from the end of a finite GP, examples 11 and 12.
Yeah, sometimes you want to count backwards. If you have a finite GP ending with term L and the common ratio is R, there's a way to find the nth term from the end.
How does that work?
The formula is dollar on $1. Think about it. Starting from the end L, to get the term before it, you divide by R. To get the term before that, you divide by R again. So to go N1 steps back from the end, you divide by R N1 times.
Dividing by R N1.
Yeah.
Makes sense.
Yeah.
Let's try example 11. Find the fourth term from the end of 8, 4, 2, 11, 28.
Okay. What's the last term, L?
L, Ln 1, 28.
What's the common ratio, R?
R N1 equals 12.
And we want the fourth term from the end, so N4.
Okay, plug into the formula. Rn1, 1, 1, 4, 1.
That's 11, 28, 12, $3.
15 tests. So $1,128 divided by 18 is the same as multiplying by 8.
So 1128 times 8, 8.
8 goes into 128.
Yeah.
$8, $8.81, $8, 88, $8 plus 48, $228, $8. Yeah.
So it's 116.
The fourth term from the end is 116, correct.
Let's try example 12. Find the fifth term from the end of 243, 81, 27, 9, 17, 29.
Right. Last term, L.
L at 1729.
Ratio R.
L air is 81243. Both are powers of 3. 243 is 3 times 5. $81 is $347. So the ratio is $34.35 is 35.3.
Good. RR13. We want the fifth term from the end, so N5. Formula. RN01, 1729, 1351, 1351, 1329.
13.5 car is 180 and $1.
So we have $1,729, $181. Multiplied by the reciprocal, $1,729 times 81.1.
And 729 is 933, or 81 times 91.
So 81 goes into 729 9 times. The answer is 19.
Perfect. You're getting the hang of working from both ends now.
It seems so. Example 13 points out another relationship involving terms from the beginning and the end.
Yes, this is quite a neat symmetry. It says if you take the kth term from the beginning and multiply it by the kth term from the end, the result is always the same, no matter which k you choose.
Really? What's it equal to?
It's always equal to the product of the very first term and the very last term, L. So kth term from start times kth term from L times L.
Let's see if that makes sense. The k term from the start is L tier.
Right. And we just found the formula for the kth term from the end. LLK.
Okay, so multiply them all times LRRK.
Renatas.
The delta one in the numerator cancels with the RK one in the denominator.
Leaving.
All times a stall. Wow. It works out directly from the formula.
It does. It's a fundamental property reflecting the symmetry of the progression.
That's elegant. Now, the source goes into a few more involved proofs in examples 14, 15, and 16. They look a bit more algebraically intense.
They are, yeah. They dig deeper into the structure. Example 14, for instance, relates terms at positions P, Q, and R, showing specific combination equals 1. It uses logarithms in the proof, actually.
Okay.
Example 15 connects geometric progressions with arithmetic progressions, where you add a constant difference. It shows if you have terms A, D, C in an AP and X, Y, Z in a GP, then a particular expression involving X, Y, Z raised to powers related to A, B, C equals 1.
Interesting mix.
And example 16 looks at nested progressions. What if certain worms, like the Q arthosated of one GP themselves, form another GP? It proves that the differences in their positions, P, Q, Q, R, RS, must also be related in a specific way, actually forming a GP themselves.
So lots of structure hidden in there. We probably don't need to walk through the algebra for those right now.
Agreed. The main point is they demonstrate the rich mathematical properties and interconnections that GPs have.
Okay, so to bring it all together, the source finishes with a summary of the key properties in section 11.4. What are the absolute must-remember takeaways?
Well, first and foremost, the defining feature. The ratio between any term and the one before it is constant. That's RUN.
TN1. Got it.
Second, that symmetry property. Yeah. The product of the wave term from the start and the nth term from the end is always OA times is constant.
Third, the geometric mean idea. If you have 3 consecutive terms, or any 3 terms A, B, C that are equally spaced in position, then $2 is a $2. And importantly, the converse is true too. If $2 equals ARI, then ABC must be in geometric progression.
$2 equals ARI too.
Key test. And finally, if you pick terms from a GP at regular intervals, like taking every second term or every third term, the sequence you create is also a GP.
That makes sense because you'd just be multiplying by $2 RUA your 3H each time.
Exactly. The ratio would be a power of the original R. Great summary. So wrapping up our deep dive, we've covered what a GP is, the crucial common ratio, RA, the all-important formula 10R, finding terms from the end, and some of these core properties like $2B and the constant product Euler.
That's a solid overview. Understanding these gives you a really good framework for spotting and working with this type of exponential growth or decay pattern.
Yeah, and even though the source focused purely on the math, it really does make you think about where else these patterns might appear.
Oh, absolutely. That's the fascinating next step, isn't it? You start seeing potential GPs everywhere once you know what to look for.
Like you mentioned earlier, maybe compound interest.
Definitely. If interest is compounded periodically, your balance gets multiplied by 1 plus interest rate each period. That's a GP.
Or population growth, maybe under ideal conditions.
Could be, if the growth rate is constant. Or even things like radioactive decay, where a substance loses a fixed fraction of its mass over a set time period that's multiplying by a common ratio less than 1.
So maybe a final thought for everyone listening. As you go about your week, keep an eye out. Think about things that grow or shrink in percentage terms. Could the principles of geometric progression be describing what's happening?
It's a great question to ponder. The math we dissected today really does have echoes in the world around us.
Absolutely. Well, thanks so much for walking us through all of that really clarified geometric progressions.
My pleasure. It was fun diving into the details. Always fascinating to explore these patterns.